like the ones we've been looking at, just a sequence of bits, that's the message, a sequence of bits, that's the key, XOR. Would that be enough? Now that is, the OTP stands for the one-time pad. And this has been around for a while. People have studied it, of course. Okay, so the basic idea with this algorithm is, again, what we've been discussing. The cipher is the encryption, key and message, and that's just equal to K XOR M. Remember, that's XOR. Okay, now the definition of a one-time pad is that it has a key. The message can be any sequence of bits. It doesn't matter, right? So remember, a message can be a movie, you know, a Netflix movie, could be a book, an encyclopedia, a set of encyclopedias, all of Wikipedia, you know, that's pretty big. So it doesn't really matter what it is. At the end of the day, all of that we know is stored as digital bits, so it's a sequence of bits. So that's defined. And then we know that the key is also a sequence of bits. But as it turns out, the OTP has an additional definition. And that is that the key needs to be a random, so notice these words because they're very heavy, very important. It's a random sequence. So it's a random sequence of bits with an additional constraint that this random sequence of bits is as long as the message itself. What do you think about that? So now you have, you know, imagine if you have a movie, a Netflix movie, and if we put that Netflix movie from beginning to end, it would be a very large sequence of bits. And now we're saying that the key, so we have a message, we have a key, and the key needs to be as long. So we have a message length is equal to key length. Do you guys see that? Now we had said in symmetric key encryption, obviously we had said that you don't encrypt the whole thing. You break it into blocks, right? You break it into blocks and then the keys are smaller. They're the size of the block, maybe 128 bits or 256 bits or something along those lines, 2046, whatever. But it's some amount. But now the OTP is saying that one of the requirements is that the key has to be equal length as the message. So what do you say about that? What's your thought, your thinking? So that's a really large key, right? So that, you know, a very large key like that might be problematic. Imagine if you have to, every time you got to do something, you have to send a key that is as big as your movie.
So it would like, this is probably really dumb, but like if you're going to chop the data into blocks, chop the key into blocks as well?
That's what we will do, sure. That's actually what we're going to do is we're just going to chop the data into blocks and then just use one key of a small size. If you took, so I see what you said. You said take the message, break it into blocks, and the key break it into blocks. But you still have the problem that whether you send the key as a whole or send the key in blocks, you still have to send all of them. You see that? So it's the equal amount of information.
Gotcha. Okay, yeah, I see what you mean.
Yeah, so that's a problem. That's a problem. Now the reason why the OTP says that this is a good thing is because if you think about it, when we do a key of blocks, let's call this one K OTP, and then K just something else. So, you know, K, some other encryption algorithm. What's the problem with this? The problem is, even though this might be fully random, right? You know, the original key might be fully random. As you start applying that same key to the whole message, what emerges? A pattern will emerge, right, guys? Because this key is the same as that one, same as that one, same as that one, same as that one. You see that? You see the problem? So even though this one might have been originally random, as you start applying it to the whole message, there is a kind of a pattern emerging. Do you understand that concept, guys? Are there any questions on that?
Yeah, I see what you mean.
Yeah, and so the reason why, so really, the OTP, this idea of the key being the same size as the message is actually like, it's the goal. That would be the goal. That would be what you would want, because the whole pattern is random in theory, right? It's fully random. And so there would be no patterns along here. And so that's, you know, would be better. Okay, so that's the intuition there. And so the question that you would ask yourself is, now that we understand this, so we can say, so is the OTP secure? Remember that idea. First of all, what do we know? First of all, we know we can't have, it's impractical to have keys as big as the full message. That's the first assumption. So really, it's not practical to do. We can't. Right? It's not possible. But if it were possible, you asked the question, is the OTP secure? Well, it is fully random. And so that also takes us to another question, really. If we want to know if the OTP is secure, well, the first thing we need to know is, what is secure? You see that? Because we're saying, oh, is the OTP secure? Well, you might ask me, but you know, how do I know if something is secure? You know, what is secure? Or, you know, what makes a good cipher? A good cipher. What makes a good cipher? You know, those are the key questions, okay? And so cryptography has been studied for quite a bit, right? It's been studied for a long time. And so this takes us historically, I'll give you a little bit of context here on the history of this. So, you know, because really that takes us to a few set of events. The first one is 1950s. Well, cryptography already existed. So let's say pre World War II and during. Right, they were already looking at the Enigma, the machine of the Germans, and also we have in England, we have Turing. I think that's how you spell it. And he developed with his team a machine that would try to break this, but their encryption was not exactly as the encryptions we're talking about. But anyway, that's historically where encryption existed. So that's, you know, kind of pre all of this. And then in the 1950s, we have two events that are really important, both of them at Bell Labs, which, if you don't know what Bell Labs is was the AT&T research lab. Okay, and so then we had two things that are actually very important for computing, which was the transistor. Okay, and then also information theory, which back then it was called communication theory. So information theory was developed by a gentleman named Claude Shannon. Okay, so he formulated a lot of things for the AT&T network related to communication. So first of all, he talked about, the reliability of communication, what was important to have reliable communication. But then he started studying, obviously, he studied other things like AI, he was interested in that, games. But one of the things that was really important that he did is cryptography. Unfortunately, a lot of the work that he did during that time is not so much well known because it's classified. So a lot of this was being done by, for the military, what is now the NSA and the CIA, right? So the NSA in particular, you probably know that they do crypto code breaking, things like that. Okay, but basically they hired Claude Shannon to kind of formulate all of these ideas. All of this was new. He had formulated a theory of communication theory, information theory, and then he was, after that, he was consulting on cryptography. And just the question was, really, you have to think about it, right? You kind of go back to the idea. What algorithms do we need? But more importantly, because you can have thousands of people creating algorithms, let's just start with the very basic one, right? If we have a message, an XOR operation, and a key, is that secure? And that took us to what is secure? What makes a good cipher? You see that? And so those are really the key things that Claude Shannon needed to establish somehow, okay? And you will see that he actually came up with something, a condition that is really interesting. Might not be so intuitive at first when you see it, but that's a definition. So that's the idea, okay? So we're trying to ask that question. Oh, this has limits, so I can't create any more slides. That's a problem. Okay, so what I'm gonna do is I can do this on PowerPoints. So give me a sec. I will create a slide. For whatever reason, I can't create any more slides. So I'm gonna stop sharing this. Okay, and I'm going to create, you guys are still there, correct?
Yeah.
Create a slide here. I should be able to write on that. Okay. Share this. Okay, so you should be seeing the slides now, right?
Yeah. Oh, yeah. Okay. I think we're good.
So I'll just write on here. Yeah. Okay, so that that should be. Okay, so we were at historically then, what makes a good cipher? What makes a good cipher? Okay. And so the basic idea is, so now Shannon and the people doing this kind of research started thinking, okay, so, you know, how can I say, you know, if something is good or not? You know, how do I define a metric or some kind of an approach that we can say that, yeah, this algorithm is good? So as it turns out, he came up with, in words, kind of this idea. So the basic idea is so here we go. So remember what's going to happen is when you send a message, and let's actually go back to Bob and Alice here. And they have, so there was an original message. There's a message over here. They have a key. And then let's imagine, you know, that's like the communication channel, something, whatever, fiber optic, wireless, you know, radio waves, or cable, right? So copper, something like that. So whatever it is, it's communication channel. And this gets tapped by Zelda. And Zelda is an eavesdropper. So, you know, you have maybe firewall here, firewall over there. So Zelda cannot go in that direction, right? And she cannot go in that direction, but she has full access to this space here. And so really the only thing that will be sent across that channel is what? What is that called? Remember, this is called a cipher. What was the definition of the cipher? Or the ciphertext?
It's the encrypted message.
It's the encrypted message, exactly. Very good. So now then, what we end up with is the basic idea is that, so remember, again, we are trying to define what makes a good cipher. That's, you know, the question we're trying to, you know, what, you know, what, you know, how do I know that what we use here is good, secure? What makes a secure, good, secure cipher? So you have to frame that in some way. So the basic idea is the ciphertext. The ciphertext should not reveal any information about the plain text. It sounds kind of trivially easy, right, to say that, but it's true. It's definitely true, right? The ciphertext, which is C, should not reveal any information about the plain text. So if you have C, which Zelda could get, she should not be able to infer M from it. And so that's, first of all, that's the original or the basic idea, okay, that you want to have. So the question is, how do you measure that? Okay, how do you measure that? You know, is there some kind of a metric, some kind of an approach? Okay. So Shannon and people like him who were working on that problem, you know, they did research, right? And they analyzed, so let's say, you know, Shannon, let's say, but I mean, you know, a lot of people, not just him, analyzed the security of the OTP, where if you remember, it is the message and the key, where message for the length, where the length of the message is equal to the length of the key. Okay, they're the same. Okay, so that's the idea of the OTP. And so they studied this question. And so the question is, you need to frame that, right? You need to frame that idea, right? And so, and how do you quantify it? And it's very difficult to quantify, actually, to do this. You know, how, you know, what would you do? Count the number of bits, you know, or what do you do exactly? And so really what Shannon did, he was very good at, his area was like, many of his areas, he had many areas, but he turned to probability. He turned to probability theory, right? And probability theory is the theory of the likelihood of things, right? So it's a metric. So I don't know if you noticed, but the key thing about it is that in probability theory, now you end up with a metric. What is the probability of something? And we know that probabilities, work in ranges from 0.0 to 1.0, right? And anything in between. So that intuitively we all understand probabilities, what's the likelihood that it's gonna rain later tonight? Well, I don't know. I haven't looked at the weather, but the fact that it's been raining all afternoon probably means that it's gonna rain. Now, some of you may have actually looked at the weather already and you know for a fact that it's not gonna rain. So I made an observation based on what I've seen. Probabilistically, I think there's a likelihood that it's gonna rain at least a little bit. If it's not raining already, because if it is raining already, then I already met that probability, but I don't know. So do you guys see my point, guys?
Yeah, definitely.
And so that's what they were looking at, right? So if you remember, the question that you're looking at before is what makes a good cipher. So, how can I take cipher A and cipher B and say, this one gets 2 checks, this one gets only 1. Which one is better? So you have to measure some kind of metric. Okay, and so that's what Claude Shannon was doing. And so he just came up with a very simple thing. I mean, I've already stated it. There's nothing more to say except that he wrote it like this. And this is probably what you'll see, whenever if you ever look for this, you'll see something like this. So this is square brackets. Yeah. So I got this and this. Now I want you guys to understand that this is not like an algebra type of equation where I'm actually, because I could probably imagine some of you are already trying to solve for one of the variables or something like that. That's not what this is doing. It's more about what this is saying. Okay, it's more about what this is saying. So let me just make sure I wrote this correctly. So I got, now let me make this one more explicit, that's 0, this one is 1. Okay, and that's, the ciphers are the same. So what do you think that is saying? And this, by the way, just means the probability. That just means the probability. So this is what they came up with as far as how do you define if something is good. An algorithm should be good if it basically meets this condition. What do you think that means? Anyone want to take a stab at it? So another way of saying this is, by definition, let's say a cipher E comma D has really good secrecy if the top condition is met. I should have written it backwards. So what do you guys think? We have to interpret that a little bit to understand it. So we have E, we have K, we have M0 and M1, we have the ciphers, and we have PR, which stands for the probability. So what do you think is the, and as I said, don't try to solve it as an equation and solve for a variable. Instead, try to interpret what that is saying. So what do you guys think that's saying?
Probabilities are going to be about the same.
Of what? Of what? You're on the right track. You're on the right track, but of what?
Of the cipher, like, result.
So so think about this. Zelda is able to get the cipher, right? We already saw that. I think it was oh yeah. Zelda can get the cipher. And what do you think this is saying? So tell you what, let's do this because it's already, I'm seeing the clock. This is a good stopping point. I'm going to leave this as, a problem for you guys to think about. Okay, think about this, and then somebody on Thursday, just tell me what it means. Okay, and maybe we'll do the same thing with bonus points. Whoever wants to go first, let me know.
Is it possible to give a stab at it really quick?
You want to do it now? Go ahead, please.
I'm just curious if this is right.
Yeah.
So a cipher ED has a really good secrecy if the probability for the encryption of one message is equivalent to the probability of a different message.
You are on the right track. It's just the way you said it. I think you get the idea. There's a slight better way of saying it. So if you have the cipher, right? That's what you have. Then a good cipher means what? That given the cipher, the probability of getting either M0 or M1 just by having the cipher is
The same, equivalent.
the same. Exactly. Very good. Do you understand now, guys?
Yeah.